Hi all, and welcome to the Emergent Vision Technologies presentation. I am John Eilert, President, CTO, and company founder, and I look to provide details of how Emergent has helped customers level up their camera systems with higher speeds and advanced processing capabilities. Some highlights about Emergent are presented here. We are a multi-award winning company with a focus on high-performance GigaVision product. We have many years shipping products at speeds of 10 gigi, 25 gigi, and 100 gigi. We have a strong focus on providing end-to-end technologies and comprehensive support for our customers' applications. Here's a quick snapshot of the adoption of GigaVision products ranging in speeds from 10 gigi up to 100 gigi. Emergent has shown how top performance can be achieved and open up many markets including machine vision and entertainment to the use of such technologies. Some companies are just now leveraging our efforts towards releasing 25 gigi and higher speed product, but still a ways to go to provide ratified, mature, and performance product. Speeds like 10 gigi, 25 gigi, and 100 gigi are a must-have in many applications. However, as we launch our new Eros 5 gigi line of cameras in 2024, we will be leveraging our deep experience in performance applications to reliably support 5 gigi and lower speeds in one or more camera per server applications, with a wide variety of performance processing options in the same zero copy and zero loss sense. With such a broad range of products, we find it helpful to chart out the various resolutions and frame rates provided. At 10 gigi, the products range from 0.5 megapixel at 1500 frames per second up to 50 megapixel at 23 frames per second. At 25 gigi, the products range from 0.5 megapixels at 1600 frames per second up to 127 megapixels at 17 frames per second. And at 100 gigi, the products range from 2 megapixels at 3462 frames per second up to 152 megapixels at 16 frames per second. For line scan, the products range from 4K at 172 kHz line rate up to 16K at 400 kHz, with a special nod to 9K TDI at 600 kHz line rate. As we launch our new Eros 5 gigi line of cameras in 2024, we will introduce many of the same sensors we already support, but now in lower speed, lower cost, and much smaller size options. While SWIR is coming to 10 gigi soon, we will also include SWIR in the Eros product line. That's a lot of high-speed cameras, so to find the right camera, you can visit the online camera selector from the Emergent website. Enter in your application critical parameters to filter down to suitable models, and review other more detailed specs by showing other columns. Finally, click on the link to go to the camera product and resource page. Works on PC or cell phone, and significantly shortens the time required to find the right camera for your application. Next, proceed to select the lens. You can visit the online lens selector from the Emergent website. Enter the sensor-specific parameters or just select the sensor model used in the camera you have chosen. Then choose the parameters for which you wish to calculate and filter lenses. Then enter the appropriate input parameters such as field of view and working distance. And lastly, feel free to filter the list further based on manufacturer or other special features. At Emergent, we see the big picture and have thus developed a high-performance camera ecosystem where all items we provide or recommend are thoroughly tested at both the component and system level. We continually push the limits of what can be achieved with minimal cost implications. We need to push the limits of the associated technologies and integrate or develop solutions to support the most challenging applications. Performance systems can be comprised of many 25 gigi cameras, talking to a few servers with multiplexing and PTP features utilized by low-cost switches. Performance systems can also be comprised of a lower number of 100 gigi cameras, talking to a few servers with the same multiplexing and PTP features utilized by low-cost switches. Performance systems can also be comprised of a large number of 5 gigi or even 10 gigi cameras, talking to a single server with multiplexing and PTP features utilized by even lower cost switches. We find that this is a pain point for manufacturers of lower speed cameras, and so we leverage our expertise in high performance systems to provide best-in-class system density alongside of lowest system cost with the introduction of the Emergent Aeros line of cameras. In addition to powerful processing engine NICs like the AMD Xilinx Alveo cards and Emergent's own FPGA-based NICs for additional functionality beyond standard NICs, we pioneered the use of Mellanox NICs for use with performance camera systems. We now have support for equivalent Broadcom NICs for addressing cost-sensitive markets. 100 GigE, 25 GigE, 10 GigE are all supported, noting that 5 GigE and lower are also supported to provide the same performance benefits for medium to high camera count systems through the use of low-cost switches. With the high-performance processing options available in GPUs and FPGA cards, one can create the lowest cost and highest density system in the industry. FlexProc stands for Flexible Processing, which is the simplest way for a user to create and test their machine vision algorithms. The user can create custom CPU, GPU, and FPGA plugins and run on low to high performance hardware systems without the need to write low-level image capture code. FlexTrans stands for Flexible Transport, which is the simplest way for a user to pass image data and results anywhere in their system, and has done so using the best-in-class zero-copy and GPU direct technologies. Combined, FlexProc and FlexTrans lead to maximum performance, rapid prototyping, and endless processing flexibility and endless scalability. Let's look at a real hardware demo as per the last animation. We have 8 cameras and they all feed into one NIC and one server, and that server holds 2 GPUs. There is also an additional server which holds also 2 GPUs. This is the hardware view. We switch now to the data flow view, and here we decide what we do with the camera data. We have 8 cameras that feed the first GPU in server 1, which passes its result to the second GPU in server 1, which passes its result across the network to the other server, where we have 2 GPUs to do further processing. For this demo, we have each GPU perform the simplified task of drawing a unique color rectangle and a unique brightness within that rectangle, and we have the GPUs perform this task for each of the cameras in the system. So GPU 1 draws the red rectangle, GPU 2 the yellow rectangle, GPU 3 the green rectangle, and GPU 4 the blue rectangle. And each GPU also applies their configured brightness to their rectangular regions. The software is not limited to such simplified serial operations, and vastly more complicated configurations are possible. This demo has a single camera using GPU Direct to an RTX A6000 GPU. We have a polarization plugin loaded to the GPU. Using the plugin parameters, we first select normal viewing of this IMX253 polarization sensor-based 10 GigE camera. We then select the polarization direction plugin option. The color hue is a measure of the angle of the polarized light. We then select the polarization degree plugin option, which allows us to see in brighter areas when the reflected light is more polarized. Let's look at how one can create their own custom plugin for use within eCapture Pro, taking full advantage of the zero copy, zero loss GPU Direct functionality while writing only plugin code. We first write our code, which is CUDA-based for the NVIDIA GPU. With eCapture Pro, we provide a number of working examples, like the polarized plugin you have just witnessed. We then compile our code, which creates the plugin DLL, which we later load within eCapture Pro. We now load the plugin DLL. We then instantiate this plugin on the selected GPU and set the plugin option for initial viewing. After connecting the desired camera to this GPU, we run the plugin and view the resultant output. The next example shows a very general purpose off-the-shelf inference detection plugin. We load the plugin, we instantiate the plugin on the desired GPU, we connect the camera to this GPU, and finally we run the plugin and watch the plugin detect and classify the cups in the scene, noting that this tracks the objects as they move. Let's now show how easy it is in eCapture Pro to rearrange the distribution of processing of 21 10GbE cameras with 3 RTX A4000 GPUs using a very simple brightness plugin. We start by directing all 21 camera outputs to GPU 1. Then we run the plugin. Note here we are using PTP for 1 microsecond sync accuracy. Next, we disable GPU Direct with a simple click to illustrate how we can easily support GPUs or environments which do not support GPU Direct. We perform high-performance copies to move images from system memory to the GPU. Let's repeat the previous test, but this time we direct 7 camera outputs to each GPU for a balanced processing distribution. And we run the plugin again. Again, we show how to configure this without GPU Direct. We note that without GPU Direct, that regardless of high-performance memory transfers, that we are utilizing 2 times the system memory bandwidth, so definitely GPU Direct is preferred. All of the preceding technologies are most commonly used with area scan cameras and have been deployed in multiple systems using AI and machine learning algorithms. But the same technologies and algorithms are also finding similar uses in line scan camera applications such as battery foil inspection. The 100 GbE Pinnacle LZ 16K G5 16K 400 kHz line scan camera is leading the way with best-in-class performance for maximum throughput. The new 100 GbE Pinnacle TLZ 9K 600 kHz TDI model is also very popular for this application. This animation illustrates a typical task of an area scan camera, which is inspecting objects on a production line. The cameras here are hardware triggered by the sensor looking for objects on the conveyor. Images are transmitted with low latency and jitter back to the computer for analysis and action. Generally, the object under inspection is captured fully in a single image. Emergent area scan cameras have 3 inputs and 3 outputs with opto-isolated and TTL options depending on your application needs. This animation illustrates the same task with a line scan camera. Generally, line scan cameras are used for scanning a continuous web of material like print or fabric, but does not preclude applications as shown here with discrete objects. The cameras here are hardware triggered by the sensor looking for objects on the conveyor. The individual lines of a given frame are triggered synchronously through the use of the continuous encoder signal shown in green. The lines of a given image are immediately transmitted back to the computer and assembled in the user buffer with zero-copy technology. Emergent line scan cameras have encoder RS422A/B inputs, 1 trigger input and 2 outputs. TDI line scan cameras are used to expose the same line on the object multiple times to allow either higher speeds with the same lighting or same speed with lower lighting brightness requirements. TDI achieves this by having multiple lines in the sensor with each line exposing multiple times, and the exposure or line rate is perfectly synchronized to the movement of the conveyor through the use of the encoder. We will now review the Emergent line scan camera implementation details alongside of some line scan fundamentals, starting with the I/O connector of the cameras, which is a 12-pin connector featuring differential quadrature encoder inputs, as well as other general purpose inputs and outputs. Here we see the general block diagram of the triggering options of the line scan cameras. Many modes are supported, which vary from full internal based triggering to full encoder based triggering for precise synchronization with moving conveyor systems. Here we see a subset of camera parameters specific to line scan camera operation, which fall into categories such as general purpose, image calibration, color calibration, external trigger control, encoder statistics, and specialized. A line scan fundamental is dark and lit FPN calibration, which falls under our image calibration category. On the left, we see contrast enhanced dark images before and after dark FPN calibration. On the right, we see lit images before and after lit FPN calibration. The graphs shown illustrate column averages, which highlight the superb correction that the camera performs with a single click. The calibration curves can be saved and loaded to eliminate the need to recalibrate when powering up the system. Our line scan cameras support quadrature encoder A and B inputs, which allow the camera firmware to detect forward and backward motion by tracking the 4 encoder phases. With mode D configured as shown, we can set the GP encoder direction parameter to allow filtering in of only forward or backward pulses. Additional camera firmware encoder features include an encoder pulse multiplier and an encoder pulse divider, which are used to synchronize the material movement with the line triggers, which can vary based on encoder model and magnification, for example. We also provide statistics counters to allow system integrators to validate the triggers post-multiplier and divider to check trigger rate and jitter characteristics. A fundamental exercise in line scan systems is to configure the scan rate to create the correct aspect ratio of the pixel. In mode A, which is an all-internal triggering method, we use the line time parameter and simply adjust the line time until the approximately correct height and width aspect ratio is observed. We can calculate this as well, of course. Note that this line time parameter does not track changes in material speed, so the user must take care of this if correct image proportions are desired. In mode D, which is an all-encoder triggering method, we need to set the encoder divider to the appropriate value to correct image proportions. This method is popular since it does track material speed without any runtime adjustments. Unlike color area scan sensors, which typically use a tight 2x2 Bayer pattern and a debayering process involving approximation through interpolation, color line scan sensors such as the one shown here have a much greater separation in the red, green, and blue channels. Every encoder cycle generates one exposure for all RGB pixels at the same instant, but these pixels are looking at different parts of the material. We need to buffer red lines and wait 4 encoder cycles before the green exposure of the same point on the material. Similarly, we wait 4 encoder cycles more before the blue exposure of the same point on the material, before finally outputting the complete RGB pixel. The G-Pixel GL5016 16K 5 micron 400 kHz line scan sensor, which we ship in the Emergent Pinnacle LZ 16K G5 100 GigE line scan camera, has special capabilities to output arbitrary rows of the 16-row sensor for specialized operations. More commonly, this is used for color imaging as shown on the right, where we grab one red, one green, and one blue line, and then simply employ spatial correction as previously shown, as well as employing color calibration using the camera's white balance and color correction matrix features to create a best-in-class color image scan. We note that this trilinear operation, that there is no approximation through interpolation like color area scan Bayer cameras, so the color reproduction is optimal. Let's now review some of the fundamentals of performance imaging, such as zero copy and GPU Direct. This short animation illustrates the triple memory bandwidth usage of a system that does not utilize a zero copy or header splitting technology. A system like this can result in data loss as memory bandwidth is exhausted. Data loss occurs when the buffer in the network card overflows when the CPU and memory do not permit further transfers. This incidentally is what RDMA proponents compare with when discussing pros and cons of traditional GigiVision and RDMA, which is very misleading as this is the worst case example. So what exactly is header splitting and why are copies needed in some implementations? A GigiVision stream is made up of multiple frames or images. Each frame is made up of a leader packet, multiple image or payload packets, and a trailer packet. All packets follow the UDP Ethernet protocol, which is an unconnected protocol. This simply means that the camera sends the packets and leaves the receiver to do its job of placing the data safely in the destination buffer. Being an unconnected protocol, this means it has zero network overhead, which leads to maximum network performance. It also means fundamentals like multicasting are supported. We must properly design our receiver to avoid data loss. CXP also follows this same protocol and leaves the receiver to its job of placing the data in the destination buffer. This leads to top performance and lowest latency and jitter with a quality receiver. I will note that the inability of some companies to design a quality receiver has led them down alternate paths. This short animation illustrates the zero-copy memory bandwidth usage of an optimized GVSP-based system using zero-copy. We see in this animation that data flows freely and reliably thanks to zero-copy and system optimization. The same approach is also used for the SMPTE 2110 streaming protocol for the massive media and entertainment market, where zero loss is also critical. Rocky V2 also supports zero-copy transfer, which is its primary benefit. Some will continue to claim this is now the guaranteed transfer mechanism, which is again false. At high speed, proper system design and margining is important to create a zero-loss system for any protocol, but we note that zero-copy is the critical first step. This short animation illustrates the zero-transfer process using GPDirect, which completely bypasses the memory and utilizes only the PCI Express endpoints of the CPU for 0% memory bandwidth and 0% CPU utilization. This short animation illustrates the FPGA card process, which completely bypasses the memory and CPU for 0% memory bandwidth and 0% CPU utilization, since all processing is done on the FPGA card. This slide highlights the point about multicast technologies. GigiVision plus GVSP is currently the only protocol which supports this fundamental networking feature. Other standards will be quickly dismissed in applications requiring efficient redundancy and distributed processing. This short animation illustrates how the data from one camera can be sent to multiple devices for parallel processing. A simple use case could even be where a separate system is used for display, while one system performs intense calculations. This slide is an illustration of how the proposed or ratified changes are converging the interface standards. USB remains mostly the same, but is a point-to-point technology. CXP has adopted the Ethernet physical layer, converging towards GigiVision. GigiVision plus RDMA and GigiVision plus TCP, if and when ratified, is converging to CXP and USB as a point-to-point technology. This is perhaps 2 years out. GigiVision plus GVSP will maintain its integrity and feature set and not converge with the other protocols. With the introduction of the use of TCP and RDMA for GigiVision image transmission, we see that for some camera providers, the use of these different protocols is creating a fragmented landscape whereby different NICs and drivers will need to be supported across the industry by various third parties. With top performance, Emergent is able to maintain the current protocol across all speeds of interface and not jump around with different protocols and NICs to support your needs. Why are packet resends used with TCP and Rocky V2, and what are the implications on jitter and latency? If a system is not well designed and tuned, then no amount of resends will allow the system to run in a stable manner and will indeed drop packets and frames. In addition, when image transfer bandwidth is slow due to poor system design, then buffers fill up. The fullness of the buffer is a measure of the system latency. The filling up and draining of the buffer is a measure of the system jitter. Both jitter and latency are important in machine vision systems, especially those needing to make timely decisions, and both are a sign of an unstable system with poor or no safety margin. What we see here are actual tests run with an Emergent 100 GigE HZ10000G camera, where we have one oscilloscope channel sampling the exposure signal directly at the camera, and the other channel is sampling a signal from the application, indicating when the image is received and accessible in the host application. We note that with a finely tuned zero-copy system, that there is no buffer backup and no need for crippling resend technologies of TCP and RoCE v2, which are really more appropriate for large file transfers than for real-time machine vision systems. What we do see is that RoCE v2 requires more FPGA resources to implement, and as such the cost of the FPGA will be higher than that of the lightweight standard and mature GigaVision GVSP protocol. This is even more so true if a resend buffer is implemented, and especially so if it's implemented in external memory on the FPGA. We see that in order to create the smallest and lowest cost camera, that these cameras from various manufacturers are not supporting RoCE v2 below 10 GigE, and some not even below 25 GigE. This is one way in which Emergent's new Eros 5 GigE offering will continue to provide true zero-copy performance, while the others rely on TCP and conventional GVSP processing, which yields 3 times the memory bandwidth and 33% efficiency of the Emergent zero-copy methods. In multi-camera systems, Emergent will remain unmatched in system density and price performance metrics. And remember that many state low CPU utilization that is actually memory bandwidth utilization that is hiding in the background and preventing maximal system performance. While RoCE v2 can provide a zero-copy solution, there is still a long list of concerns regarding its applicability to machine vision applications, of which proponents will not make you aware of. Which of these are applicable to your particular application can be unique, but we present a fairly exhaustive list for convenience. I will state that all items listed have been noted by our current customer base and have thus decided RoCE v2 is not appropriate for their applications. On the other hand, we have yet to have a customer which we have not satisfied with our solutions, and nobody matches us on performance, support, and price. Since Emergent was founded back in 2007, our focus has been on performance and multi-camera applications, with a strong focus on the big picture, which is developing the highest performance, highest density, lowest cost solutions, and providing processing options which answer the question of what do we do with all that camera data. I wanted to provide a few examples where customers have come to us reporting a poor experience with another vendor's high-performance camera product. In one such recent example, we have 20 times 5 GigE cameras on a single PC. 2 major camera manufacturers could not resolve drop frame issues. In another example, we have 5 GigE cameras on a single PC. Over a 2-year period, the vendor made many attempts to resolve drop frame issues, but never could. In a final example, the customer is trying to run 8 10 GigE cameras on a single PC. The vendor's comments were that they have never tested more than 2 cameras per PC. All of these customers are now happily using Emergent product. There are 2 very disturbing problems here. One is the poor performance some vendors are offering for their high-speed camera product. The other is that a vendor would actually sell multiples of 8 cameras without having a discussion about what the customer's goals are to ensure the product can meet their needs. Our cameras are everywhere you care to look. We dominate in certain spaces where adoption rate is more rapid. We believe other spaces will follow, especially where factors such as performance, cost sensitivity, system simplicity, and time to market are at play. As you can see, Emergent has the highest performance camera portfolio, and we keep our overall product portfolio focused. We innovate, develop, adapt, and expand the markets we enter, and have the foresight to do so. Please do contact us for further details, and we appreciate you taking the time to view our presentation.